So I'm drawing a disk of mass m and radius capital R, and let's say that the mass is uniformly distributed, so there's a mass density m over the area, which is pi r squared. That's the density of this disk. And let's say that it's rotating. There's a hole here, there's an axis through there, there's no friction, it rotates at an angular speed omega naught, and let's say that we want the kinetic energy of this object. So we know that the easiest way is to use rotational quantities. Instead of thinking of 1/2 mv squared, we should think of 1/2 I omega squared. But let's see how much more difficult this is if we insist on 1/2 mv squared kinds of things. So if we do that, then we need to recognize that the closer we are to the center, the slower the speed. So if we divide this up into little annuli that are concentric annuli, so there's a tiny little width there, and there's a length, which is the circumference. This thing, the further that annulus is from here, the faster the speed, and that relationship is just v equals omega naught times r. So the edge travels at a linear speed of omega naught times capital R. So, in other words, we're integrating, so we're thinking of doing the kinetic energy as an integral of 1/2. There's a tiny little bit of mass in that green annulus, and so whatever that is, we have to figure it out. We're going to multiply by its speed, which is going to be determined by how far that annulus is from the center of the circle, v squared, and we're going to integrate this kind of a thing all the way from an annulus that's right at the center there, distance 0, all the way to an annulus right at the edge, which is capital R. And so we need the dm, and the dm comes from the density, right? So it's the density m over pi r squared times the infinitesimal region over that has, but that is the area of this green annulus. So every green annulus has a tiny area, which is the circumference, which depends on how far the green annulus is from the center. So 2 pi r times dr. So if we open that green annulus out, we would have something like this. We would have a line like that, which has length 2 pi r, and extension here would be dr. So the area would be 2 pi r times dr of that annulus, of that little ring. And so we have, this becomes an integral of, we have our dm, we're going to have our v is given by this, so we have m over, there's a 2 there, pi r squared times 2 pi. All of this is constant, so 0 to r. I have r dr, but I also have v squared, so that brings an omega naught squared here and an r squared, so we have an r cubed there. So this gives us m, 2 pi's cancel here, I have an r squared that survives, I have an omega naught squared there, and then I integrate, I get r to the 4th over 4, and this gives me a kinetic energy of m omega naught squared r squared over 4. Okay, but it took a bit of an effort to figure out what the dm is. So that's the kinetic energy of this object. It's m times the speed at the edge squared over 4, because the entire thing isn't moving at speed omega naught capital R. Let's do this from the perspective of just replacing mass with moment of inertia and linear speed with angular speed. Right? So what are those quantities? In this case, we know that the moment of inertia is of a disk is m times the radius of the disk over 2, and the angular speed is omega naught, so it looks like that. And straightforwardly, we have the same thing without going through any complications.